I think we'll return to the sort of simpler DIA stuff that I was doing yesterday morning. It seems like most of the people are returning and have some clue of what we were doing yesterday morning. So I think that's a good opportunity for us to continue with that. Uh, and we'll get to see how the background proteome gets used again in some new ways. But so we think of just building a spectral library from your search results. DDA, you can do all kinds of fractionation, everything, and in the end, you build a spectral library. And then, so the assay libraries to me sort of mix these two problems. One is just like all this getting all this prior information into one place so that it can be used as a library, and then picking the coordinates that you're going to use to actually query the data. So an assay library is both, right? It's basically a transition list, but it also loses some of the original information, like what was the originally measured retention time? Show me all the noise in the spectra. It's very specific for its purpose. So Skyline allows you to build a spectral library, and then you can, as you've seen, you can choose different. You can say, oh, I want 6 transitions, or I want to allow neutral losses, or I don't want to allow neutral losses. So like the Bruder assay library, the big tabular file that we imported, they chose to allow neutral losses. If I now want to say, no, I don't want to use neutral losses, I've got to go back to their original search results. It's not like I can just tweak some parameters and all of a sudden. So that's what happens in Skyline. The Bruder data actually comes with a max quant search, and that's what they built their library out of. But they built what? Yeah, so they took a max quant search. So yeah, let me show you that. So this is the SSD I've been talking about that has all the information on it. But it's probably like 300 gigabytes total. Um, so yeah, so here's the SSD. So I was preparing it in. Um, so yeah, so this is in the Bruder data. Here's the DDA data. And so you can see that here's all the raw files, and here's this is the FASTA file, 2 of them, I guess. So a FASTA for human. This is a UniProt human FASTA, plus the experiment. So we looked at it at the end. We looked at the CVs, because a lot of what gets searched and looked up is background, right? So that's the UniProt background is human, or the background is human, and we can use this. They search this UniProt human FASTA to find all that and everything, but then they also spiked in some proteins, and that's what Mina is going to look at in terms of when we do MS stats analysis. Is because they spiked them in at various concentrations so that they could look at how well they could quantify those proteins. So and then here are the max quant. Wait, where are the max quant results? I guess I have to go to this is my other computer. I didn't actually copy the max quant results on there. I guess I don't know. So on my other computer, I expect somewhere here to find, where should I put the max quant results? I guess I have not copied the max quant results, because I do go, yeah, I gotta go back to here, maybe. That's the course. My cost, profit, Bruder, DDA. Yeah, so I never copied the max quant results, but here they are. You can see I got zip files, and then, so yeah, this is a max quant search. Yeah, these are the indexes. I guess the combine is going to have, so that's the MQ-PAR XML, which Skyline uses and then what you would point Skyline at is going to be in this text folder, is this MSMS text file. So Skyline can build a library out of an MSMS text file. So that would be, yeah, I mean, we can actually maybe start that off. Let's go start a version of Skyline on this is my desktop. I'll just do, so I have never done this experiment. I've been meaning to do this experiment, and actually, and what I find is that people, when they do DIA, they don't necessarily put up all the, they put up the assay library, but the assay library has already lost a lot of information, right? Because if they chose neutral losses, or they make these choices, and then you can't unmake those choices because all you have is the assay library. So whereas in Skyline, we try to put everything into the blib file, that's the library file, and then the choices you make about how to measure it, whether you want 5 transitions or 8 transitions, or you want to include neutral losses or you don't, or you want to, all those kinds of choices you make in Skyline with settings. Okay, so if we go to settings, peptide settings, and then library, we can do build, and we'll go this way. This is going to be Bruder. I guess we'll just call it Bruder 2015. And we're going to have to actually put it somewhere. So let's actually build it to that folder where I found the MaxQuant results. So there, we're going to build a library in that folder. And we'll keep the redundant library, and we'll have a cutoff of 0.99. Now, when you decide a cutoff, you really need to know something about the probability values, because some probability values, like Skyline's always using a probability value, but if it's an adjusted probability value, like a Q value or something, then this number corresponds well to false discovery rate, which we use a lot. But if you're using peptide profit, then it's a posterior error probability, and frequently a 0.9 posterior error probability actually produces a lot less than 1% false discovery rate. So, you have to think a little bit. This making this cutoff choice is one of the most important choices. I think we can say that we expect these to have IRTs in them. So we can, because it's data coming from Biognosis, so I think we can say that we expect the Biognosis IRTs to be in these examples. But again, I've never done this, so this is how I would start trying to set this up. And then now, when I go to add files, I would go into MaxQuant searches, standard sample set, and combined, and text, and this is this MSMS text file, and I would just open that. And then I would try building a library out of that. And this is the assay. This is the Bruder assay library. But this is my Bruder 2015, and it's reading the MSMS text file. And MaxQuant actually organizes its data really nicely. So building a library is very quick, even for a fairly large library. So we can actually sort of sit here and watch it. You can see down in the. That's what's going on, and it should be done fairly quickly now. Yeah. Oh, actually, it's got to read. Oh, it's still reading the spectra pretty quickly. So it's processed the search results, and now it's reading spectrum files. But yeah, they're gonna be raw spectra, right? And then that gives you a lot more flexibility. And now it's filtering. That might take a while. Okay. Well, we can come back to this. Any other questions? Yeah.
Processing your data to generate like high quality spectral library.
Huh?
Can he use like a Python script kind of upstream of this?
Yeah. And then he also said, well, it's probably just easier to use Skyline. But he's, yeah, I mean, I think that's really still so one. Yeah, so I think that's still a good manuscript because it talks about how to set up the instrument, what kind of samples to use, how, and then it even maybe gives some suggestions of. So again, they're mixing like or their end product is one of these types of assay libraries, right? It's actually an Excel spreadsheet that's so yeah, Bruder, uh, this MCP. So yeah, this was I kind of skipped over this yesterday. I guess we can go a little deeper now today. Um, so this is the supplementary material from the paper, and so yeah, there's actually a legend and micro tissue. There's a bunch of different things, but what we've been doing is this profiling standard sample set. So they did multiple experiments in the paper. We've been focusing on one of them, and so here's what goes by the name of an assay library. It's really just a modified peptide sequence. This is unmodified charge state, protein ID, protein description, is proteotypic. I don't even know. I don't know that gets used, but and then there's a precursor, MZ, an IRT, some information about what fragment it is, whether or not what kind of loss there is. So you can see that there's a fair number of, uh, you know, B4 with a water loss. It's like, well, is that the most likely thing to be measuring for a quantitative experiment? And then fragment charge, fragment MZ, and then the library. This is the library. This is the spectral library part. This is the relative ion abundance, and it looks like they're actually for relative ion abundance. No, I guess they are normalizing to 100, maybe. I don't know. Well, yeah, because you can see that most of these things have a value that's 100. So that means they're normalizing the most intense ion to 100. So you lose any visibility into how good were these spectra that we're pulling off of. So this is a very processed view of a norm relative rank. I don't even quite know what this is because it doesn't start at 1. Maybe it's. Oh, here's 1. Yeah. So, but I mean, yeah, but this one you don't even see 1 in this first one. So I think maybe that has something to do with what the original spectrum contained. So yeah, but you notice that this first peptide doesn't include a value that's 100 or 1. What? Yeah, but number 11 is the next one. So yeah, no, so no. Here's what I think is going on. I think they're normalizing to the most intense peak in the spectrum, and they're giving that 100, and then they only choose peaks in the spectrum that match the targeted peptide. So there's just this came from a spectrum where the most intense peak is an unidentified peak, right? They could. Yeah, something like that. Yeah, exactly. So there's a lot of choices that have been made upstream, and I mean, I guess you can read the description of how they did this. I don't think it's as detailed as they're telling you this necessarily, but to me, these assay libraries, that's like the Skyline document, right? And you're losing the actual library that just has all the spectra without any choices made. So that's what we're trying to capture here in Skyline. Wow, and I guess filtering this takes a long time. So we'll come back to that later today. So yeah, it's typical. So in the DIA, so most people will, like if you're doing with Skyline, you just include your Skyline document, then you have everything. But if it's typical to include this library, because this is the really the end results of like, okay, this is what I'm searching. So you kind of have to include this. It's the transition list, but it's not always typical to find that they gave you all the information of how they got there. So since I'm frequently reprocessing these data sets, I find that I have to contact authors. I know them all, and I say, hey, can I get the max quant results? I think in this paper they actually included the max quant results because they're part of the analysis, so it was easier. But yeah, multiple papers now from the Aebersold lab, I've had to say, can I get the PEP XML and the MZ XML that you built the library out of? And I've run across people who are like, I don't have that anymore. That came from so and so. And it's like, and so now you've lost this, I think, sort of important artifact of like, okay, how you search the data and what you came up with, and uh, so I'm working with. Yeah, actually, we're having an MCP standards meeting the day after ASMS this year. So we kind of recognize we worked with Steve Carr over at the Broad Institute to form a new standard for targeted proteomics when you're doing SRM and PRM, anything where you're actually choosing your targets before you measure, and obviously they have standards for DDA, and now we realize, okay, that we're falling behind on DIA standards. There's not really enough. But yeah, so that's when somebody tells you, oh, building quality assay libraries or spectral libraries, to me, I feel like all the information about how to measure peptides and their spectra that are useful is totally useful, and you would use that for Skyline too. The actual tools and processes for coming up with one of these things, you can use this thing in Skyline because they're in the field, so we made Skyline handle them. But the Skyline workflow is much more like actually what we can do in maybe this last half hour is we'll go back. I mean, I think it's sort of what you did in the tutorial, where you build a library in Skyline and then you use Skyline settings to choose the transitions. And that's also what we'll do later today with the CelebSec dataset, because the CelebSec dataset, I thought their assay library was just too permissive, I feel like they were trying to get really large numbers and not thinking enough about how to measure things really well. So I just wanted to go back to, the data is great. I wanted to go back to the starting point. So I got their search results and built a library out of that. Yeah, I think that was one of those ones where they use an earlier, so the Aebersold lab in that paper would tell you to use Spectrast to build your library, and some of the older versions of Spectrast were extremely permissive on neutral losses and things like that. And yeah, so all right, so that's that. Yeah, so let's go back to the while Skyline figures out how to get a non-redundant library, because that's obviously a large library, and yeah, it's going to take us. It'll probably take the next half hour to get that library. What? No, that's on my desktop, but we don't make at that point. We're not. I don't think we're making huge use of parallelism, but we might be able to. So we might be able to speed that up. I don't know. I forget why that's so slow. Um, okay, so where are we? Okay, so I think for this part we can just start up Skyline. Um, and Let me see. Oh, I gotta get it. Here, different set of notes to follow. So I kind of walked you through there's two proteins. Yeah, here we go. Two proteins imported. So I'd walked you through this two proteins example, and we're looking at how, okay, there's, you know, we have the full gradient, 80 minutes of chromatograms to look at in every case, and sometimes we felt we got, that looks like a pretty good match. There's there's definitely some nice and easy data here, and it might actually be enough if we just wanted to quantify this protein. This might be enough information to go out and quantify it, because it's like, I mean, I feel like there are enough peaks here that I see that I would be willing to trust as measuring this protein. So one thing you have to ask is, how many peptides do you need to measure a protein? And so if all I wanted to do was measure these two proteins, this might actually be enough, right? Because I could throw out a bunch of these and keep the ones that have nice data and then go measure it. But I want to show you another way. The next. So this is the incredibly naive way of starting measurements with Skyline, and I think for these two proteins, we probably could come up with enough peptides that measure them pretty well that we would be fine. But let's look at how, so we've already started venturing into, IRT and retention time normalization and much larger data sets. But let's take the next step into, there's a fairly easy way. If you just did some DDA measurements, even if you didn't have IRTs, if they were done on the same system, then they probably have very similar retention times. And so I showed you that example where we got a library from Biognosis, and the correlation with our predictor was like an S. So it's not, but Mike has shown you that, in our lab, we're doing these now, gas phase fractionation DIA runs to recalibrate the retention time, and then we get a lot of extra power by having extremely consistent retention times, but they're not totally necessary. And so what we're going to do is we're going to build our own library, and we're just going to use the retention times in the DDA runs to tell us a range smaller than 80, 90 minutes that we should extract to look for the peptide. Because it's like, well, okay, it might be 3 or 4 or even 5 minutes off, but if we have a window of 5 minutes, then, or a window of, we get to decide how accurate we think it can be, and Skyline will just go ahead and use the actual measured retention times in your DDA as a prediction of where to find the peptides in a DIA run. So as long as you did your DDA runs fairly close to your DIA runs, you may not need retention time alignment, although retention time alignment will get you much more accurate. So let's go. So I'm assuming that not many people have this new two proteins imported Sky file. We're going to start fresh. So go ahead and click new, and then if you haven't already chosen default, go ahead and choose default and no, so that we're just all on the same page. And we're going to create a new document and go through the next level. We're not, this is a document that we're not even going to run a model on, and we're not trying to do IRTs. So we're going to go to settings, transition settings, and we'll switch to full scan again, because that's what we want to focus on, full scan, and we're going to pick count And now at this point, I would probably just use centroided, but I'm going to stick with the tutorial because it was written before we had centroided, because we're going to be looking at Orbitrap data. And at this point, most of us look at Orbitrap data with centroided spectra. And in fact, our lab has started collecting DIA data in centroid only mode. It leads to much smaller files. Definitely, I know that people using Bruker instruments are doing that because Bruker has really huge profile data. Yeah, so we're going to use, yeah, we're looking at it. We're going to do MS1 extraction. So that's what this MS1 filtering is. MS1 extraction, and we're going to use the resolving power of 35,000 at 200. And then we're going to be doing DIA for the MSMS. Again, Skyline automatically chooses Orbitrap, but it chooses a really high resolving power. We're going to go with 17.5. Oops. 17.5 at 200. And so now all we need to do is get figure out what the isolation scheme is. And we're going to go ahead and add a new one. And this time we're gonna use, again, we use pre-specified windows, and we're just gonna import it out of some data. So go ahead and click import. It's my new favorite way to get get isolation schemes. After having some mistakes, I was like, okay, I just have to make Skyline be able to get this so that it's never wrong. Because we got a data set from Bruker where they told us their isolation scheme, and then when we eventually, it didn't work right, and we eventually looked at the data, and we were like, you actually mistyped one of the windows. And luckily, it was one of the windows near the end, so we just pretended that the isolation scheme had a narrower range than it actually had. Okay, so the raw files are in this DIA intro, so we haven't gotten through the intro yet. And then DIA tutorial and raw, and there are two, and we're gonna import them eventually, but we're just gonna choose one to get the isolation scheme out of. All good? Everybody found that file? Okay, so click open. Skyline takes a moment to actually get that file open and read its isolation scheme, and then, so here it is. So this is pretty much 400 to 800 with optimized windows. So that, I went through how to create. Does anybody remember how to create that if you were creating it from scratch? You didn't have a measured file? Then you would click calculate, and you'd go 400 to 800, and you don't need to follow along with this. 20 MZ windows, and then optimize window placement. And if I click OK, it doesn't change any of the numbers because this is exactly the same thing. We can click graph and have a look at the graph. And you can see that's the isolation scheme. If you zoom in on a point in the isolation scheme, I'm doing that with the scroll wheel, you can see that the boundary of the isolation scheme is not a whole number, right? That's the optimized window placement. We're putting the boundaries where peptides don't usually go. And that's why it's okay not to have margins, right? Because there's some region, the peptide's it's not gonna fall on the boundary, and it's gonna fall probably about at least 0.33 MZ away from a boundary. If we're measuring charge 2 and charge 3. So yesterday, does anybody remember how high the charge was for Bruder? We went up, no, we went for charge, we went up to 7. Yeah, so you wouldn't want to use optimized window placement if you're going to measure charge 7, but it's questionable whether you should be measuring charge 7. So Like overlapping demultiplexing? Okay. So yeah, so that would be, yeah, you would just go, you know, I want to measure 400 to 800 with 20 MZ and deconvolution is going to be overlap and then optimize window placement. And so now you're going to get 20 MZ windows and you get a longer list. People don't do this because I'm just going to have to go undo this. And then if I graph that, now you can see that there's this overlapping, and then we can use, I think Mike probably mentioned it, we can use computational methods to deconvolute this so that it looks like we use 10 MZ windows. And that's, you know, that's great. And you can see that that's different from, it says show single cycle overlaps and show gaps. So that's just Skyline highlighting potential problems in your isolation scheme. So I'm going to go back to 400 to 800, 20 MZ with optimized window placement without overlap. And now if let's say if I went here and I said, well, I'll go to 25, and then I go here and I go, actually I start at 45, that should give me both a gap and an overlap. So yeah, so you can see here Skyline's highlighting the fact that, well, you know, you appear to be measuring the same region twice without any sort of demultiplexing that you're going to do or anything, and then you actually have a gap in your measurements, which is what we had with the Bruker data we got. But yeah, so you can turn those on and off, and yeah, if you turn that off, then you can see the gap better. I don't know, maybe you can see the overlap better too. I don't know. So we'll close that, and I guess I'll just recalculate them one more time, and then we'll move on. Optimize window placement. Okay, and we'll window type. There's measurement and extraction. And when we're doing optimized window placement, they're the same thing. It's only when we have a margin that they're changing, right? So yeah, if I wanted to go 800, 400 to 800, and I want to use 25 MZ windows, and I want to have I want to actually have extraction windows of 25. So this is measurement windows. To get extraction windows of 25, I need to have 26, right? But if I go to extraction, then now I can say I want to have 25 MZ to extract chromatograms out of, versus 25 MZ that the instrument measures, right? So there's two concepts, and we actually started, I don't know, we started with one concept, and enough people, I was like, yeah, the developer who did this wanted to start with the extraction windows because he was thinking about extraction. I was like, no, mass spectrometrists are going to be thinking about what the mass spectrometer measures. And so in the end, we decided to allow you to look at both. And so there, I just did this with no optimization. This is a fairly typical type of isolation scheme. And now you'll see I go 4 to 425, 425 to 450. Those are extraction windows. And then if I switch to measurement windows, I've actually started at 399.5 to 425.5, and then 424.5. And then if I graph this, now you can see the margins, and the margins are like, we're not going to extract chromatograms out of those margins. The instrument measures them, but we don't extract chromatograms out of them because those are regions where the instrument doesn't measure very well. And so, yeah, and so then if you turn this off, this is what we're extracting from. You can see there are no gaps or overlaps really other than these margins. So that's the concept. The blue is all 25 MZ, and then we have a half an MZ on either side. And so that's measurement versus extraction. Yeah, actually, if I turn this off, does it say extraction windows? Yeah. So when I turn this off, it says, okay, these are your measurement windows and those are the margins. And then when I turn this off, it says, hey, I'm now showing you the extraction windows. So, all right, so I guess I was wrong. We don't have an undo button here. Calculate 400 to 800, 20, optimize window placement. Okay. So we're good to go here. We'll call this 800 to 420 MZ opt, and I might have already done 400 to, not 800 to 400, 400 to 800, and I'm gonna stick hands-on at the end so that I don't get a conflict because I might have already defined this. So click OK. There we go. Now that's our isolation scheme. And we want, yeah, so we're going to stick with, we're going to use MS IDs. And I guess in this tutorial, we're going to say that we want 2. So we're pretty confident that our MS IDs are very close to our peptides. So we're going to extract only 2 minutes on either side of the MS IDs. So everybody have their full scan settings looking like that? So yeah, you get to choose how much chromatogram you want to have. But if you miss your peaks, that's not necessarily good either. Okay. So click OK, or wait, did we click OK? Do we want to go look at other properties? Yes, we're going to go to trans setting. Oh, actually, so let's do this. Okay, so we're going to go OK, click OK. We're done. And now we've just defined our isolation list. If we don't need to define any targets yet, we might want to go measure some DIA, right? So this is where we'd go File, Export, Isolation List. And we would tell it that we want to export for ThermoQ Exactive. And click OK. And this, this would be, again, you would name it 400 to 820 MZ CSV. I did this yesterday, and you could see what the isolation list turned it out to be. So you're welcome to go ahead and export an isolation list at this point. I'm just going to cancel out. But then now, okay, so we exported an isolation list. We measured some DIA. Now we want to start defining our filters. So we're defining our query coordinates that we're going to query our DIA data with. So let's go back to transition settings, and we'll go to filter and say charge 2 or 3 precursors, charge 1 ions, and YBP. So YB and precursor ions. We're going to allow ion 3 through the last ion. And we're not going to treat N-terminal to proline that's special at all. And we're going to go ahead and turn off use the DI precursor window for exclusion, because we feel confident about our fragmentation. Our fragmentation is not going to leave a lot of stuff around. And that's it. So, you can see actually that we have, okay, in our spectral library settings, before we build our spectral library, I think Yeah, so for our spectral library settings, we would like to say that we want 0.1 MZ, which is still really, this is DDA measured on an Orbitrap, so that's still really huge. I frequently use 0.05 for DDA Orbitrap match tolerance. The default in Skyline is 0.5, and that's really for, you know, low resolution LTQ type MSMS spectra. So you have to think about when you did your DDA, where did you measure the spectra? Are they high accuracy, high resolution spectra, or are they low accuracy spectra? And then you set this value based on that. We're gonna say 5 transitions. We can also set a minimum. And let's go ahead and do that, say minimum 5 as well. And then in this case, so we can do it just from the filtered ion charges and types, which would mean that we would pretty much ignore this ion 3, in which case we would want to go here to the instrument and change the instrument range to be higher. We can go ahead and do that anyway. So we can, you know, Ben said that they use 350. The Bruder paper seemed to use 300. And then we can say our max MZ is 2000. And then go back to library, and now, but we're still going to go ahead and say we're only going to use the filtered product ions. Did people follow all of that? I can go back through it. This 0.11, this 0.1 MZ, do people have an idea of how big that is in ppm? How many ppm? It's at, well, if you're, yeah, I guess if you were using, if you have 1,000 MZ, it's going to be 100, it's going to be 100 ppm tolerance. Yeah, so that's why I will usually use 0.5, because that's more likely to be like 50 ppm or so. Anyway, okay, so do people have, okay, so filter, we've got 2, 3, 1, YBP, ion 3 through last ion, no special ions, and don't use the DI exclusion window. For library, we have 0.1, use a library spectrum, choose 5, and then choose the 5 from the filtered product ions. And then our instrument is 300 to 2000. And again, this instrument range only applies to the MSMS spectra, right? This doesn't apply to the precursors, because the precursors are filtered based on our 400 to 800, right? Everybody got all that? Good, okay, so we click OK. And now we have to go to settings, peptide settings. And we're going to build a library, so just switch to the library tab. And we're going to click build to build the library, and we're going to call it yeast DDA. Skyline gives us a default name, but we need to tell it where to save this yeast DDA. So just click browse, and DIA intro and DIA tutorial, and I guess we can put it in spectral library. Actually, let's put it up at the top. Spectral library. That's where the data is that we're going to put in the library. So put it in DIA intro, DIA tutorial, and it's yeastdda.glib. People have that? Click save. We have to choose a cutoff. We're going to choose, so in this case, I know that this is this is a library built with Sequest and Percolator. So Percolator uses a Q value. So this, if I use 0.99, that will give me a 1% false discovery rate. And there are no IRTs here, and we're not gonna try to include ambiguous matches. So click next. What? I tend to keep it. I mean, it can be fairly large, but having the redundant library can be useful because it's got all of the spectra that were matched so it's, yeah, it's a record. And if we ever want to add anything to this library, we need the redundant library. So the redundant library is sort of like the real record of what was searched, and a non-redundant library is, but yeah, this tutorial actually says not to keep the redundant library, but I tend to always keep it. And it's just a matter of preference. It's not like you have to keep it. It's just more information. So you get to decide. It depends on how you feel about your disk space. So yeah, for this tutorial, you can turn it off. We're not ever going to come back to this library. So, and then the next thing we want to do is add files. And now we'll go into that spectral library folder. And you can see that we have a choice of several things, but we want this all.perc.xml, which is the combination of these two SQT files. So we just choose that and click open. And so now we're ready. And we can just click finish. Skyline will start building it. We'll build it very quickly, and then it gives us a message saying, hey, there were ambiguous matches, which is okay, fine. We knew that we didn't want to include ambiguous matches. And does everybody understand what an ambiguous match is? Okay, that's where the search engine has taken a single spectrum and it says, hey, I think it's this, and I think it's this. So it could be generated by a chimeric spectrum or something like that, but it's not, I wouldn't say it's something that you want to save in a library as your canonical representation for a peptide. So that's why we tend to exclude them by default. If you're doing label-free DDA quantification, you want to keep them probably because that's your only hope of quantifying those peptides in the MS1 space. Yeah, but you could quantify both of them. I mean, like you could, anyway, I mean, no, it will use both of them. It would add both of them to your target list, and then it would go look for both of them, and then it would say it, But anyway, yeah, you might not want to. But anyway, we made it optional. There is a checkbox. If you had the checkbox checked, you wouldn't get this message, and you would just get extra identifications in your library. And yeah, maybe not the greatest thing to use those, but we had enough people asking for it so that we went ahead and did it. Okay. All right, so let's keep going here. We're getting, so I guess luckily I'm the one who goes next, so I'm just going to run a little bit long on the morning session because it doesn't look like absolutely everybody's here yet. So let's keep going to where we can actually import some data here. Okay, so that's it. So we're good. We've built our spectral library. Let's go have a look at it. Wait, are we done setting settings? Oh, let's go set our background proteome too. Okay, no, let's go look at our library. Okay, so click OK. And then now if we go to view spectral libraries, this is our spectral library. Did everybody check that spectral library? I didn't really call that out, but. So is everybody looking at this spectral library now? Or at least the people who were here this morning? So you might not have B ion. There are various things that you might not. You could turn on charge 2 ions and B ions over here. You could also choose to show the precursor. There might not be a precursor though. And then you can sort of look at the quality of these spectra. Some of them look good and others not so great. And I'm told that this was actually not the greatest data. You can see that there are only 11, there's only 1,000 peptides found in this, even though that's yeast, that's a pretty small number of peptides. So it's not that great data. You can click this ... button up here and you can see some information about how many spectra got matched, not really that many spectra either, 2 data files. You can see that they used a percolator Q value with a cutoff of 0.99, and then you can see that one of the files actually only identified 40 spectra, and only 20. Yeah, so we've got 2 files, but one of them was really terrible, and the other one was kind of okay. So this is not great data, but we're playing with it anyway. Yeah, what? You click on this little ... button to get that. And that's just the, and that all, this is nice because it records the files that you used and the cutoff score, and then it gives you some insight into what you got from both. And then another thing that's important to look at is down here. It tells you the file the spectrum came out of, and it also tells you a retention time. And so when you're checking your library the very first time, you want to make sure that it has reasonable retention times. It might not have retention times at all, which means that you need to contact us and we'll work out why your search engine, or why we're missing the retention times, or your search engine isn't reporting them. And then search engines report retention times in a variety of seconds and minutes. And so we have to do special, basically divide by 60 anytime that there's seconds, so that we get minutes to show. So there are some times where you might have measured, a 90-minute gradient, and you'll see times that are like in the thousands. And that just means that the times were recorded in seconds and we didn't know about that. So any of those things happen, contact us and we'll work with you to get them fixed. They're usually pretty easy for us to fix, but we need to know about them, and you need to be sort of conscious enough of what you expect in a library. And one of the things is that your time is in the right scale. So now that we know that we have that, that's a good thing. And we could, at this point, just go click add all, and that would, tell us that there are 96 peptides that don't match our current settings, but we could just go past that. And then it says, okay, this operation is going to add 1,128 peptides, this many precursors, and about 10,000 transitions. And then there were 11 unmatched, and we can add them all, but it's just going to add them to this one big list. It's called library peptides, and we'd rather have them associated with our proteins or with their proteins. So if you did that with me, just click undo. And then now we're going to go back and add because if I say associate proteins and then click add, it'll say, hey, you need a background proteome. So, okay, so now we're going to go make a background proteome. So we go to settings, peptide settings, digestion, background proteome, and we have this yeast, or I have this yeast forward and reversed, but we want to not forward and reversed. So click add, and we'll call this one just yeast. People following that? Those who are interested in it. And then we're gonna go to USB intro DIA tutorial, and we'll save it here, and we'll just call it yeast. and save. Skyline takes a moment to create the file, and now we have a yeast ProTB with 0 proteins in it, and all we have to do is add the FASTA file. Are there people still following? In DI intro, DI tutorial, there's a FASTA file, yeast contam FASTA. And you can go ahead and open that, and Skyline will read it and create a background proteome out of it, which is just a database with lots of information about the FASTA for fast lookup. So it tells us that there were 87 repeated protein sequences, and those were just merged. All right, so well, we're 5 minutes over, we're 8 minutes over. Who would like to move on to the main session for this? We did not actually get our targets, and we don't actually have another day to continue this. But we should probably get on to the main event of analyzing larger data sets. But this is how you would build this. I now have a yeast background proteome. I could add all from here, and it's actually matching the peptides to the current document settings. It's also matching the peptides to the proteins, and now it tells me there were peptides matching multiple proteins, and I'll say I don't want to add those, and then 96 peptides not matching the current filter settings, and I'll say, yeah, I don't want to add those either, and then click OK, and Skyline tells me that this is going to, now instead of just one big list, it's going to add 270 proteins, and I could add these all. And so now these are the query parameters. You know, this is my, you know, my assay. Now I built a library. I've got a spectral library, and you know, all these peptides are matched to spectra, and you can see they're full spectra. And yet you can also see that if you expand them, I've only included the precursor, 3 precursor transitions along with 5 fragment transitions, and the 5 fragment transitions are going to be the 5 most intense transitions in these spectra. So that's the 2 parts. We've got this spectral library, and I can change that at any time. I can say, oh, actually, I would rather have transition settings library. I want to have 6 transitions because, you know, I just read a paper that says 6 are better than 5. There you go. You add 6. It's very simple because you have the full library behind you. And you have retention times, and when we do extraction, it's just going to extract based on those retention times. We haven't set up any IRT library or anything, but we can still even build an mProfit model, and it wouldn't contain an IRT normalized retention time prediction. All right, so let's just take a quick break and come back at 9:15, and then we'll start with we'll first open the floor to questions about the Bruder data, which we wrapped up with yesterday, and then we'll move on to the CelebSec data set, which is the other publication data set, and then eventually we're going to get to Mina talking to us about how to actually do some quantitative queries against those and learn some stuff about quantitative statistics on these large-scale data sets. So, all right, let's go ahead. Anybody who came here this morning and got this far can go ahead and save their document. All right, so 5-minute break.